Hello. Once again, just like the last week's, you can see infinity behind me. Whoa! Infinite Noemis. Okay, so what we're going to be looking at today is the LÖVE game framework. So, this is a very small, very flexible little framework. You use the Lua scripting language, and yeah, you build your core game loop, you run it, and the Lua communicates with the C++ engine in order to run your game. So, some important stuff. LÖVE is licensed under zlib/libping. That means costs nothing, and you can use it freely for commercial purposes with no limitations. And the source code is on GitHub. We don't really care about that because we are the simpleton users who just want to make some games. So, when you want to make games in this, you have a couple of options for text editors. And I think one of the better ones is Xerobrain Studio. It's an IDE, gives you code completion, syntax highlighting, live coding, code analyzer, and debugging support. And it can connect directly to the LÖVE engine on your computer if you have it installed. You can install it right here. It's also available on Mac and Linux. So you want to go to download, and you can choose to donate if you want. You don't have to. You click this link if you don't. So I've already downloaded this, but I figured I'd show you that. Okay, so what does it look like though? Here are some examples. So you've got a function LÖVE draw. The LÖVE draw is what they call a callback function. We'll be getting into this stuff later. And this will print out hello world to the screen at the coordinates 400, 300. The coordinates, think of it like a grid, except I believe in this engine, as with most game engines, the y-axis is reversed from what you might expect. So you do have to consider that. And you can draw images, play sounds. Well, that's all well and good, but that's not making a game. So how do you make a game with this? Well, one tutorial series that is supposed to be pretty good is the Sheepolution series. And you can see the URL in my address bar over here. It is sheepolution.com/learn/book/contents. And this will teach us how to love. Because it's February and Valentine's Day is coming up, and we don't know how to love yet. So, let's fix that. We can start here with the introduction. So there's a lot of background text here. I'll give you some quick highlights based on a quick scan of it. Okay, so this tutorial is for people who want to learn how to program. That means that over the course of this session with me, we will be programming. We're not just going to mess around with visual editors. We're actually going to go deep into the thick of things and code some stuff. So, the reason you would want to use LÖVE is LÖVE is very beginner friendly as far as programming games goes, but provides all the functionality to make professional 2D games. That means it's great for beginners and experienced users. The important thing to know is that LÖVE is a framework, not really an engine. The engine is the thing under the hood that runs everything. But LÖVE, you're just coding some instructions for it. You're not actually touching the engine at all. So that means there's no built-in level editor. You have to do stuff yourself. But the upside is that you will know exactly how pretty much everything you do works, with the exception of a couple of things the engine itself does that are kind of black boxes you don't really need to know unless you really want to be a power user. So this is going to be for people without any programming experience, which will be great for us because I'm sure some of you people watching know how to program, but some of you won't. So this will be a good way to get everybody up to speed. So let's see, what other highlights are there here? Okay, I think that's all you really need to know from that. But to summarize, this is a programming tutorial that uses LÖVE because it's very easy for beginners. So here's a couple of GIFs, examples of what we'll be doing. Just a few simple things, some animation, some mathematics. We might not be able to get through all of these tutorials, but I'll try to go through what I can. I've already prepared and set up a little environment for us, which I will show you in a bit. Next, installation. I've already briefly gone over this stuff, so I don't think we will need to. If you really need these instructions, you can go to the tutorial yourself. Okay, so let's get into it. So, the first thing we need to learn about is variables. I believe I've discussed variables before in some of the previous Let's Make games, but it's good to have a review because there may be new people in the audience, and it's always good to review this stuff. So, I will, as usual, I will read for you. So, with programming, we can do arithmetics. What's 3 plus 4? It's 7. Okay, well, let's test that. We can use print to make the number appear on our output console. So, if I go over to my IDE, I'm using Xerobrain Studio here. I have a little example program here, and we can run that. And as you can see, it outputs some text here. So that's all good and well, but we want to make some outputs. So I will zoom into the output console here so you guys can see what's going on. And we'll follow this. So the first thing we want to do is print free plus 4. So we will print free plus 4. And if I do that, it will provide the output when the application closes. So we get 7. Cool. Now what is A plus B? Well, it could be anything. That's because A and B don't have a value. Let's change that. So, let's say A equals 5 while B equals free. And then, if instead of free plus 4, we print A plus B, we should get the output 8, which we do. So here, A and B are what are called variables. A variable is a word in which you can store a value. Number free is always free, and 7 is always 7, but a variable can be anything you want it to be, hence the name variable. The word in which you store a value can be almost anything. Sheep, test, pants, doesn't matter, can be anything, as long as it follows a couple of rules. So, variables are case sensitive. That means that when you have the same word but with different casing, it's not treated the same. For example, sheep, sheep, sheep are 3 different variables, each with their own value. You can do more than just summing up numbers. You can do subtraction, multiplication, division, and exponentiation, among other operations. So for numbers with decimals, you can use a dot, like so. Okay, now take a look at this. First, we say x equals 5. When we give a variable a value, we call that an assignment. We assign 5 to x and 3 to y. Next, we assign x plus y to z. So now z equals 8. Remember that you can always check the value of a variable with print. If we were to change the value of x or y after z equals x plus y, it would not affect z. It would still be 8. As you can see here, x equals 5, y equals 3, z equals x plus y. That means z equals 8, x equals 2, y equals 40. So these values are different, but if we print z, instead of 42, we still get 8. That's because z is not x plus y, it's just 8. The values are not bound, it simply drops the value that this expression results in into the z variable. It does not say watch x and y, and if they change the value of z too. That is not how variables work here. So, strings. A variable can also store text. As you can see here, text equals hello world. This is called a string because it's a string of characters. So you can connect strings by using 2 dots. This is called concatenation. So if you have one variable name equals Daniel and one variable age equals 25, you can insert these values into a different variable by combining them like so. So if we have text equals hello, my name is name and I'm age years old, this will output for us hello, my name is Daniel and I'm 25 years old. So there are a few naming rules as mentioned for variables. First of all, your variable may have a number in it, but not at the start. So test state, that's good. T8st, fine. 8 test, no, don't do that. Do not do that. Your variable name also can't include any special characters like these ones. And finally, your variable name cannot be a keyword. That is just a word that the programming language has in reserve, that it uses itself. So you have a list of example keywords here. There are a couple more, but Lua doesn't have a ton of them. It's sort of on the side of being lightweight. So you shouldn't run into that problem too often, but you do have to be careful about some keywords that could have common use with what you want to do. So, how do you use variables? Well, they can be used to keep track of things. For example, you can have the variable coins, and every time you pick up a coin, you can do coins equals coins plus 1 to increment the value. So, in summary, variables are words in which we can store a value, like a number or a text. You can name them whenever you want, with a few exceptions. Variables are case sensitive. Okay, so next we're going to go over functions. So, with functions, we can store pieces of code. This allows us to execute this code whenever we want. Functions are also known as methods. I will say to clarify, functions are generally called methods when they exist as part of a class, which is something we'll go over later. Usually, functions that are just out in the open, not attached to an object, are just called functions. But some people use these words interchangeably, and it's not necessarily wrong. I'm just saying that's a very common use case for the words. So, there are two ways to create a function. You can say example equals function print hello world. This will kind of store the function in a variable. In the more common way, function example print hello world. So you start by writing the keyword function, followed by the name of the function. A function is a type of variable, so the same rules apply as when you name a variable. The function's name is example. After the name, we put parentheses. This will be where you put any arguments for the functions, which we'll go over later. Now we can start typing the code we want to put inside our function. In this case, we put in print hello world, which prints the string hello world to the output console. When you're done, you close the function with an end. Note that when you run the code, you'll see no hello world in your console. This is because we still have to execute the function. We execute a function like this. This is usually called calling the function or a function call. You type the function's name followed by parentheses, and in the parentheses you can put any arguments you want to send to the function. So, parameters. That's another way to put arguments. So we have some code here. We have the function sayNumber that takes a variable called num. And what it does is it prints, I like the number num. So if you give it a number, like 15, it will output, I like the number 15. Button 2, it says I like the number 2, and so on. So inside the parentheses of the function, we can put what we call parameters. Parameters are temporary variables that only exist inside the function. In this case, we place the parameter num, and now we can use num like any other variable. We execute our function multiple times, each time with a different number, and thus each time we print the same sentence, but with a different number. The number we put inside the parentheses is what we call an argument. So, in the first function call, we pass the argument 15 to the parameter num. At the end of our code, we print num outside of our function. This gives us nil. And this means that num has no value. It's not a number, or a string, or a function. It's nothing. Because, like I said before, parameters are variables that are only available inside the function. So, return. Functions can return a value, which we can store inside a variable, for example. You can return a value by using the return keyword. So we have a function here called giveMe5 that returns 5. And if you assign that value, if you assign the function to a variable, after calling it, you get back 5. As another example, you have the function sum that takes the variables a and b, and what it returns is a plus b, the sum of a plus b. So, often you want to execute certain code in multiple locations. Instead of copying that code each time you want to use it, you can simply add a function call. And if you want to change the behavior of this function, you only need to change it in one location, which is the function itself. This way, we avoid repeating code. Don't repeat yourself. It's one of the most important programming principles. That is called dry. You want to be nice and dry, because if your code is wet, don't work so well. You know, in cartoons when you pour water on a robot and it short circuits? You don't want that to happen to your code, so keep it dry. Okay, in summary, functions store code that you can execute at any time. We call a function by writing its name followed by parentheses. We can put values inside those parentheses. These values are passed to the function's parameters, which are temporary variables that only exist within the function. The functions can also return a value. Functions remove repetition, and that is a good thing. But I will say, importantly, that you should be designing your functions well. Because if they don't cover what you need, they aren't going to be very useful to you. So, now we finally get into the meat of things. We'll finally start using LÖVE itself. So, what is LÖVE? LÖVE is what we call a framework. Simply said, it's a tool that makes programming games easier. LÖVE is made with C++ and OpenGL, which are both considered to be very difficult. The source code of LÖVE is very complex, but all this complex code makes creating a game a lot easier for us. For example, with LÖVE graphics ellipse, we can draw an ellipse. This is the source code behind it. And you don't need to know what this is doing. Just take a look at it, see how complex it is compared to a single line of LÖVE graphics ellipse. Much longer than that, right? Much more unwieldy. And this is what LÖVE is doing for you. It's abstracting a lot of common game features so that you only have to call these methods to access them. You don't need all this junk. You don't need it. All you need is the stuff LÖVE provides to you. Stuff LÖVE extends out into Lua. That's all you need to make games. So then, how about Lua? Lua is the programming language that LÖVE uses. Lua is a programming language on its own and is not made by or for LÖVE. The creators of LÖVE simply chose Lua as the language for their framework. So, I can briefly tell you why the Lua language would be attractive for a game engine like LÖVE. So, one of the key advantages of Lua as a scripting language is that it interfaces very well with C family languages. So, I believe how it works is that you use it kind of like a stack, if you know what that is. So every instruction is a layer in the stack, and you can pull data from that stack. So in C++, you read a Lua file and you put all of the data from it into a stack, and you pull an item from the stack until the stack is empty. So if that's confusing to you, that's okay. But it's just a brief overview of how these languages interface with Lua and why they are commonly used. You might know a lot of modding tools use Lua scripting. I believe World of Warcraft plugins use Lua. It's very common in modding and extensions of games because it's pretty easy to use, has some simple, easy to use features, it's lightweight, and it's very performant with C family languages. So, anyways, to get back to this, Lua is the programming language that LÖVE uses. So, what part of what we code is LÖVE and what is Lua? Very simple. Everything starting with LÖVE is part of the LÖVE framework. Everything else is Lua. So, these are some functions that are part of the framework. You have LÖVE graphics circle and LÖVE graphics rectangle. And everything down here, well, that's just Lua. So, how does LÖVE work? LÖVE calls free functions. First, it calls LÖVE load. This is where you want to create your variables and initialize the game. After that, it calls LÖVE update and LÖVE draw repeatedly in that order. These are your two basic game loops. LÖVE update is for your game logic, and LÖVE draw is for your graphics. These are separate so that if you have inconsistent frames, the game logic loop can continue on as normal, while your graphics loop continues to struggle. So if your draw loop is having trouble because of graphical bottlenecks and other factors, the update loop should be unaffected. So, behind the scenes, LÖVE calls these functions, and we create them and fill them with code. That is a callback. So, you write a function, and the program calls it for you. If it doesn't exist, the program doesn't bother calling it. So, LÖVE is made out of modules. LÖVE graphics, LÖVE audio, LÖVE file system for some examples. There are about 15 modules, and each module focuses on one thing. Everything that you draw is done with LÖVE graphics, and anything with sound is done with LÖVE audio. So for now, let's focus on LÖVE graphics. LÖVE has a wiki with an explanation for every function. Let's say we want to draw a rectangle. On the wiki, we go to LÖVE graphics, and on the page, we search for LÖVE rectangle. There, we find LÖVE graphics rectangle. And I can pull up a tab, and as you can see, there's LÖVE graphics rectangle. And this gives you all of the parameters and gives you little explanations for them. There are often multiple valid versions of the function, each having different argument sets. So for example, this one contains information about the x and y axis radii, or something like that. Radii, radiuses is not the right plural form. Anyways, and you have segments. So you have a normal rectangle and a rectangle that can have rounded corners. There are a lot of functions like this that have multiple possible configurations, so it's worth looking up. Okay, back to the tutorial. Page tells us what the function does and what arguments it needs. The first argument is mode and needs to be of the type draw mode. We can click on draw mode to get more info about this type. So as you can see, the draw mode controls whether shapes are drawn as an outline or filled. And you have two constants you can use, fill or line. So if you want to draw a filled rectangle, you can do the following. In the function LÖVE draw, LÖVE graphics rectangle, fill. So Let's copy that and try to use it. So we have a love draw, and we have a rectangle. It uses fill mode, and we want it to draw at 100, 200 on the screen. The x coordinate 100 and the y coordinate 200. And we give it a height and width of 50 and 80. I believe this is the width and this is the height. 50 width, 80 height. So if we run this, we see our rectangle over here. And this is drawn every single frame, because Love Draw is run every single frame. The functions that Love provides is what we call the API. API stands for Application Programming Interface. You can read the Wikipedia article, but it simply means the Love functions available to us. So, in summary, Love is a tool that makes it easier for us to make games. It uses a programming language called Lua. Everything you use that starts with Love is part of the Love framework. And you can use the wiki to learn about how to use Love. So next, we will start moving a rectangle. So, first we need to write up the callbacks. We have 3 different callbacks that we'll be using here. We'll want love load, love update, and love draw. I'm sorry, it's a little awkward for me to use my keyboard when my microphone is right in front of me, but I will make do. Okay, next we draw a rectangle. So in draw, we want to make a rectangle that uses the line filling behavior, x coordinate 100, y coordinate 50, and we want 200 height, 150 width. So if we run this, we see our rectangle up here. So this is important. The second and third argument of this function are the x and y position. X means horizontal position on the screen. 0 is the top left side of the screen. Y is where you might get tripped up. Y means vertical position on the screen. 0 is the top side of the screen. Usually on graphs, the Y value starts at the bottom and moves up. However, in graphics programs like Love, Y begins at the top of the screen and moves down. So keep that in mind when you're trying to place stuff. Okay, now we want to make the rectangle move. It's time to start thinking like a programmer. What needs to happen in order for the rectangle to move to the right? Well, the X position needs to go up. 100, 101, 102, 103, 104, etc. But we can't change 100 to 101. 100 is just 100. So we need to have something that can change to the number that we need it to be. And that will be of course, a variable. So in LÖVE load, we'll create a variable called x, and x will equal 100 to begin with. And we replace the x value here with the x variable. So now we have a variable as part of an argument. So every time this is called, it could possibly have a different x value. It depends on the value of the x variable. Remember, this isn't just being run once, it's being run every single frame. So, functions don't care about variable names, only their value. Now, we want to make the rectangle move. We can do this in the update callback. Every update, we want to increase x by 5. In other words, x needs to be the value of x plus 5, and that's how we write it. So in update, we say x equals x plus 5. So if we run this now, woo, our rectangle goes right off the screen. So, there's a moving rectangle, but there's a problem here. If we run the game on a different computer, the rectangle might move with a different speed. This is because not all computers update at the same rate, and that can cause problems. My computer's on the medium fast side, so it runs that pretty fast. Someone else might run that slower, or even faster than me. So, the example they give, say computer A runs with 100 frames per second, and computer B runs with 200. That means that in 1 second, X has increased by 500, while on computer B, it's increased by 1,000. Luckily, there is a solution to this, and that is delta time. When LÖVE calls LÖVE update, it passes an argument. If we add the parameter dt to our callback, we should be able to access it. So, let's do that. If we print dt here, we will get an output that tells us what delta time looks like on our computer. As you can see, it hovers roughly around 0.006 or so, going up to 0.007, going down to 0.005. But it stays roughly around that ballpark. That's the delta time. That's the time that's passed between now and the current update. The previous and the current update. So this delta time is different for each machine that runs the program. And it can be different under different circumstances. For example, if the user has a lot of programs running, the delta time might be higher. So, by using delta time, our rectangle will move with the same speed on all computers. All we need to do is multiply what we already have by the delta time. And if we play our thing again, moving nice and slowly now. And it will move at roughly that speed on any computer. So what we've done with this is that we've changed this from something that is modified every frame to something that takes this value. No, a better way to put it is we change this from something that will have this result every single frame to something that will be x plus 5 every single second. So it sort of standardizes the speed at which your game runs. So, a summary. We use a variable that we increase on each update to make the rectangle move. When increasing, we multiply the added value by delta time. Delta time is the time between the previous and current update. Using delta time makes sure that our rectangle moves with the same speed on all computers. So now we will go over if statements. With if statements, we can allow pieces of code to only be executed when a condition is met. You create an if statement like this. If condition, then code end. So you have the if keyword here, you give it a condition, and then run this code if the condition is true, end. A condition or a statement is something that's either true or false. So 5 is greater than 9 is a condition. It's a condition that will always be false. So we won't do this now, but if you wrap the update code that we just made in a false if statement, then it will never be run. So what we will do though is say if x is less than 600, then run that code. So what that will do is after that value reaches, what was it, 600, that's a little slow, hold on. So once this reaches 600, there we go. Once it reaches 600, execution of the code stops. It no longer loops. This statement blocks this code. And it no longer runs. If the condition were made true again, the code would run again. So, if you want to check if a value is equal to another value, you use two equal signs, like this. So, for example, 4 equals 7. And that, of course, would be false. Keep in mind, one equal sign assigns values, while two equal signs compares them. So x equals 10 will assign the value 10 to x, while x double equals 10 will compare 10 to x. And if x equals 10, x double equals 10 will be true. Otherwise, it will be false. You can also use greater than or equal to and less than or equal to check if values are higher and equal or lower and equal to each other. So 10 less than or equal to 10 is true. 15 greater than or equal to 4 is true. So a variable can also be true or false. This type of variable is what's called a Boolean. So let's make a new variable called move with the value true and check if move is true in our if statement. So we can say move equals true. And then check if move is true. And if move's true, we move by 100 a second. Move is true, but so our rectangle moves. But move equals true is actually redundant. We're checking if it's true that the value of move is true. Simply using move as a statement is good enough. So all we need is if move then, and what happens here is since move equals true, it's the same as saying if true then. But since move's a variable, we could change that value to false at some point, and in that case, this code would no longer be run until the value of move went back to true. If we want to check if move is false, we can put a not in front of it. If not move, then this suit is black not. So if we want to check if a number is not equal to another number, we use a tilde. So if 4 not equal to 5, then this is true. 4 is not equal to 5. Therefore, the code is run. You can also assign true or false to a variable with a statement. So if you have move equals 6 is greater than free, what you get is move equals true. Now that doesn't seem very useful like it is here, but remember, either side of this statement, or both, could be variables. And you can do a lot of cool stuff. Get rid of a lot of excess if statements by doing this. So it's a good thing to know. If we check if move is true and then change move to false inside the if statement, it's not as if we jump out of the if statement. All the code below will still be executed. So we say if move then, move equals false. Print, this will still be executed. So, let's make the rectangle move based on if we hold down the right arrow key. For this, we use the function LÖVE keyboard is down. Notice how the D of down is uppercase. This type of casing is called camel casing. You start the first word in lowercase, and then every following word's first character is typed in uppercase. This type of casing is also what we'll be using for our variables throughout the tutorial. So we can pass the string right as first argument to check if the right arrow key is down, which we shall do. If LÖVE keyboard is down, right, then end. So now, what happens if we launch the program? Well, if we press the right button, as you can see, we move our little rectangle to the right. You can also use else to tell the program what to do when the condition is false. So, if we make it move left when we don't press right, by using an else, what does that look like? Well, it looks like this. Every time we let go of the right key, it starts moving left. Oh dear. Okay, so we can also check if another statement is true after the first is false with an else if. So let's make it so that after checking the right arrow key is down and it's not, we check if the left arrow key is down. So instead of just saying else, we want to do else if LÖVE keyboard is down, left, then move left. So if we do this, we stay in one place, we can press the right button, move right, left button, move left. And now we have movement. So now we are going to try to make this move on the y-axis by ourselves. So if the keyboard button up is down, what? We're all topsy-turvy here. Then what we want to do is set our y variable that we just made to 100 times dt. And we can also do another else if or down. For up we subtract actually. Because as I said, that's how the grid works for us here. 0 starts at the top. So if you want to go to the top, you got to get closer to 0. And you do that by subtracting. Okay, so we've sort of imitated the code up here, down here. We use the same sort of else if. So if I press right, I go right. If I press left, I go left. If I press up, I go up. If I press down, I go down. So what happens if we press multiple keys? If I press right and left at the same time, I will go right. If I press up and down at the same time, I will go up. Why is this? It's because right and up are the if statements. So they are executed with priority over the else if statements. But if I press right and down, it will do both of those just fine. Similarly, if I press left and up, left and down, right and down, right and up, the diagonals work fine because there aren't if else if statements separating them. They are simply two different if else if blocks. Okay, so moving on, we can also use and or. So with and, you can check if multiple statements are true, like so. If 5 is less than 9 and 14 is greater than 7, then both statements are true. Both of these conditions must be true. This is so sometimes you in logic you use what's called a logic table, and the and or are very important there because those are our primary logic constructs. So if you say x and y, that means x must be true and y must be true for the expression to be true. However, with or, the if statement will execute if any of the statements is true. So if you say x or y, then if x is true or y is true, the statement is true. There are logic tables for all sorts of things you can think of. And the and or keywords are very important to them. So it is good. I do recommend learning a little bit about logic before going into programming because it does factor in a lot. You use much more logic than you ever do math. A lot of math stuff you can just plug in algorithms other people have figured out. But for logic, you really gotta know this stuff for yourself. It's not super hard. You should be able to get it pretty easily. It's very intuitive. It is, as you might say, logical, but it is very, very important to programming. So I do recommend learning about it. So to be more precise, if statements check if the statement is not false or nil. So with if statements, we can allow pieces of code to only be executed when a condition is met. We can check if a number is higher, lower, or equal to a number or value. A variable can be true or false. And this type of variable is what's called a Boolean. We can use else to tell our game what to execute when a statement is false, or else if to do another check. Okay. So next we will be going over tables and for loops. So tables are basically lists in which we can store values. If you're aware of other programming languages, you may know about structures like arrays and dictionaries. Tables are kind of a mixture of a lot of different data structures. You can use them like you would an array. You can use them like you would a dictionary. You can mix and match those use cases as you want. They are very simple, very complex, depending on how you use them. So, you create a table with curly brackets. So, if I go into function load, we will tabula rasa our program. If we go into love load and do that, we have created a table. This is all you need to do to create one. Now we can store values inside the table. There are multiple ways to do this. We could put the values inside the curly brackets. So, apples, bananas, we only have one, apple, banana. We can also use the function table insert. The first argument is the table, and the second argument is the value we want to store inside that table. So let's insert a pair, table insert, fruits, pair. And that should give us our table. So, if we try to print this, so first let's test our print function. As you can see, prints text to the screen like we expected. So, what we want to do is access the values of our table, and we do that by writing the table's name, followed by brackets. And inside the brackets, we write the position of the value we want, which is also known as the index. So, in the current state of our table, fruits 1 would be apple, fruits 2 would be banana, and fruits 3 would be pear. Something you might notice if you're a programmer in other languages is that the index starts at 1. This is fairly unique to Lua because it was originally designed for non-programmers, and they wanted to make these tables pretty intuitive. So instead of starting at 0, which they felt would be a little weird for non-programmers, tables in Lua start at index 1. So definitely be careful about that. It can trip you up. Tables in Lua start at index 1. Tricky. Okay. So, tables are a list of values. We added apple and banana first, so those are on the first and second position on the list. Next, we added pear, so that's on the third position in the list. On position 4, there is no value yet, since we only added free values. So, if we want to print apple, we have to get the first value of the list. So, that is fruits 1. I'm going to show you briefly what happens if you try to put 0 here. You put 0 there, bad argument, because it's just going to give you nil. There's nothing there. So, you start at 1. Now we want to draw all free fruits. We could use print free times, each with a different table entry. That is something you can do. But imagine if we had 100 values in our table. That would suck to do, right? Writing one of these lines 100 times. So, there's a solution to this. For loops. A for loop is a way to repeat a piece of code a certain amount of times. You create a for loop like this. So, if we say for I equals 1, 10, do print hello I. If we do that in the output window, you get hello 1 through 10. So to create a for loop, first you write for. Next, you write a variable and give it a numeric value. This is where the for loop starts. The variable can be named anything, but it's common to use I. This variable can only be used inside the for loop, just like with functions and parameters. Next, you write the number to which it should count. So, for example, for I equals 6, 18 do, we'll start at 6 and keep looping till it's at 18. There's also a third optional number. This is by how much the variable increases. For I equals 6, 18, 4 do would go 6, 10, 14, 18. With this, you can also make for loops go backwards with -1. Our table starts at 1 and has free values, so we will write for I equals 1 free do print fruits. So we simply do print fruits I. And I will put the I here. So if we do that, when we close the program, you see 1 is apple, 2 is banana, and 3 is pear. Awesome. Yeah. So, what if we add or remove a value from the table? We'd have to change the 3 into another number. For that, we use number fruits. With the number sign, we can't get the length of the table. The length of the table refers to the number of things in the table. That length would be 3 in our case, since we have 3 entries. So, if instead of 3 we say number fruits, it should do the same thing, but if we put goblin in our fruits table, this will still work fine. See? Free goblin. Let's get rid of that. Goblin isn't a fruit. Okay, so now we can draw all free fruits. We won't need this anymore. Instead, for I equals 1, number of fruits, do print fruits I. However, if we run this, you will see it's drawn all the fruits in the same place, and that makes a mess. So, what we want to do is modify the y coordinate so that it draws at a different position for each text based on the number held in the I variable. If we run this again, you'll see they're displayed like this. Much better. So if we were to add pineapple through a table insert, pineapple, then the table still draws right. We can also remove values from our table. For that, we use table remove. The first argument is the table we want to remove something from, while the second argument is the position we want to remove. So, if we want to remove banana, we simply say table remove 2 from fruits. And now we no longer have a banana. When you run the game, you'll see that banana is no longer drawn and that pear and pineapple have moved up. That's what remove does. Remove automatically changes the index of values after what has been removed. So, We had an apple, banana, pear, and pineapple. We got rid of the banana, so pear moves to banana's old position, which was 2. And then pineapple, similarly, moves to where pear was. So everything moves so that there is no empty space in the middle of the table. You can also add or change the values inside the table directly. So table can be so apple can be changed into tomato. So we can say fruits1 equals tomato. Okay, back to the for loops. There is actually another way, and an easier way to loop through the table, and that is through an iPairs loop. So, this for loop loops, or what we also call iterates through all the values of the table. The variables I tells us the position of the table, while v is the value of the position in the table. It's basically a shorthand for fruits I. For example, in the first iteration, the values for the variables I would be 1 and v would be apple. In the second iteration, I and v would be 2 and pear, respectively. But how does it work? Why does the function iPairs allow for this? And that's for another time. For now, all you need to know is that iPairs is basically a shorthand for the numeric for list, for loop. So let's use iPairs for drawing the tables. So for I fruit in iPairs fruits do print FRT. So that gives us an easier way to access the value, because instead of directly calling the fruits table, we instead put the iterated value in this variable so we can use it here. So first, I is 1, which will be tomato. So this will print tomato. As you can see here, we have tomato, pear, pineapple, as expected. So, in summary, tables are lists in which you can store values. You store these values when creating the table with table.insert or with table name 1 equals some value. We can get the length of the table with number table name. With for loops, we can repeat a piece of code a number of times. We can also use for loops to iterate through tables. Okay. So, objects. In the previous chapter, we used tables as numbered lists, but we can also store values in a different way, with strings. So, we're going to remove the fruits of our labor here. And now we are going to make our rect and give it a width. So what we have now is a table behaving like an object. So tables are not just for lists of values, they are also for objects. So width in this case is what we call a key or a property. So the table rectangle now has the property width with a value of 100. We don't need to use strings every time we want to create a property. A dot is the shorthand for table name property name. So instead of rect bracket width, you can just say rect.width. So let's add some more properties. We'll add an X, a Y, we'll modify our width and give it a height. So now that we have our properties, we can start drawing the rectangle. We want to use line fill. And instead of numeric values for these, we instead simply give it the properties of our object. And we'll also make it move. So we add a speed property. And in the update function, we change X by adding speed and implementing delta time. So we watch this, we see that our rectangle is moving. So now we have a moving rectangle again. But to show the power of tables, I want to create multiple moving rectangles. For this, we're going to use a table as a list. We'll make a list of rectangles. So move the code inside LÖVE to a new function and create a new table in LÖVE. So we'll create a function called createRect. And we'll move all this code in there. We'll make a list of rectangles here. And at the end of this, we want to insert into the table our rect. So now every time we call createRect, a new rectangle object will be added to our list. And that's right, a table filled with tables. Let's make it so that whenever we press space, we call createRect. We can do that with the callback LÖVE key pressed. So we say function LÖVE key pressed. Key. And if our key is space, then what we want to do is create rect. So whenever we press a key, LÖVE will call key pressed and pass the pressed key as an argument. If that key is space, it will call create rect. So now we have to change our update and draw function. So we want to use I pairs on our list of rectangles. And instead of rect, we're using V. And in draw, we need to do something similar. So IV in I pairs, list of rectangles, do lists and instead of rect, we're using V. So if we start this, we got nothing, but every time we press space, a new rectangle is created and drifts to the edge of the screen. Okay, so we know that works well. So that was a lot of code in a short tutorial. So a summary of what's going on. In LÖVE load, there's a table created called list of rectangles. When we press space, LÖVE calls LÖVE key pressed. And inside that function, we check if the pressed key is space. If so, we call the function create rect. In create rect, we create a new table. We give this table properties like X and Y, and we store this new table inside our list of rectangles. In LÖVE update and LÖVE draw, we iterate through this list of rectangles to update and draw each rectangle. So an object can also have functions. You create a function for an object like this. Table name.function name equals function, or the more common way, function table name.function name. So we can store values in tables not only with numbers, but also with strings. We call these types of tables objects. Having objects saves us from creating a lot of variables. Drinky. Okay, so with multiple files, our code will look more organized and easier to navigate. Create a new file named example.lua. make sure it's in the same folder as a new and empty main.lua. So we will be clearing this, and we shall make a new file, example.lua. So inside this file, we'll be creating a variable. So we have that test equals 20 to the script. But now, if we go into main Lua and try to print test, what we will see that the output is nil. That's because the program does not know that example.lua exists. It just assumes, oh, there hasn't been a test variable defined, so that must be nil. So we want this program to recognize example.lua. And how we do that is using a require. So, for example, if we say require example here, now the output is right. It recognizes that example.lua exists and runs it. So what happens is a variable is created called test with the value 20. So I guess one way to think about it is, imagine if you copied this and pasted it where the require example is in this code. That's basically what we're doing here. So you can also put it in a subdirectory, but you do need to include the whole path if you do that. So test in this case is what's called a global variable. It's a variable that can be used anywhere in the project. So the opposite of that global variable is a local variable, or a local for short. You create this by writing local in front of the variable name. So if we were to make this into a local variable, what would happen to main? Well, now it's nil again, because this is local to the script it exists in, so main doesn't know it exists. All it knows is what's on main, because this is only local. So local variables are limited to their scope. In the case of test, the scope is the file example.lua. This means that tests can be used everywhere inside that file, but not in other files. So, if we were to create a local variable inside a block, like a function, if statement, for loop, then that would be the variable scope. So, if we say if true, then local test equals 20. End. print test. Tessie. If we run this, we should get nil twice, yes. Because this is nil and this is nil. Because the test variable is localized entirely within this block, just like the Aurora Borealis was localized entirely within Seymour's kitchen. So, parameters of functions act like local variables. They only exist inside the function. So, to really understand how scope works, take a look at this code. So, we have test equals 10. Let's mimic this here. Test equals 10, require example print test. And here we have local test, which is 20. Come on, get big. There we go. That should be easier to read. Okay. Function. Some function. Test. If true, then local test equals 40, print test and print it outside of that. So we have a bunch of prints, and they should give us totally different values. Yeah, exactly. See? So we can see what the code is doing here. So first, we set test equal to 10 in main.lua. This is the global variable. So then we require example, which is basically the same as taking all this code and pasting it here, except there's some scoping involved. It's as if we took this and put it into a block here rather than just pasting it wholesale. So the first thing that happens here is that the test variable is set to 20. We define a function here, but we do not activate it until here, where it's called with the value 30. So this is run. If true, then local test equals 40, print test. So as you can see, the first print statement gives us 40 because this test prioritizes looking for local variables first. It looks at the most local variable in scope before anything else, and the most local variable in scope is this one right above it. So after that ends, we print test again, and this time this test is the same as this test, and when we called the function, we set this test to 30 right here. So that's where the 30 is coming from. The 30 is being plugged in here, and then that trickles down to this test here. So after that's done, we print test again, and the test that still exists in this scope is up here. So the value of test down here is up here, 20. And then we're done with this script, so we move back to main and print test again. And the value of test that's local to main.lua is up here, test equals 10. Hopefully my explanation of that made sense. Okay, so if you run the game, it should print 40, 30, 20, 10. So I outlined the code, so we won't need to do this. If you add a return statement at the top scope of a file, so not in any function, it will be returned when you use require to load the file. So, for example, if our example.lua has local test equals 99 and return test, when we have a require will be equal to this return value. So, in this case, test, which equals 99. So this will be 99. And if we print it, we would get that. Okay, so the best practice is to always use local variables, and there are multiple reasons for it. First of all, Lua is faster with accessing locals than globals. Now, if you'll recall, when I was talking about how Lua interacts with C, I was talking about a stack. And this is why local variables are faster. It's because they're at the top of the current stack. So think of it as a bunch of plates. Like, if you have a pile of plates stacked up, it's much faster to take a plate off the top of the stack, right? If you want a plate off the bottom of the stack, imagine that you can't lift the plates up, but you have to take them one by one. If you want a plate at the bottom of the stack, it's going to take a while. If you want a plate at the top of the stack, it's going to be immediate. You can get it right away. Lua exists in C++ as a stack, so local variables will always be a lot faster. And that's the gist of it. It's a little more complicated than that, but hopefully you understand just a little bit more about how Lua and C++ interact. Okay, so another reason is that with globals, you're more likely to make mistakes. You might accidentally use the same variable twice at different locations, changing the variable to something at location 1, where it won't make sense to have that value at location 2. If you're going to use a variable only in a certain scope, then make it local. So, I don't think there's that much wrong with using globals if your game kind of warrants it. Basically, if you want values to stick around for a lot of different scenes in your game, then I think it's okay to use globals. But one of the things you should be doing is you should be sort of containing them within objects at least. So you have, for example, you could make a game object where you store global game variables. So instead of just having like screen width and screen height out in the global namespace, you instead can stuff them into your game object and have game.screen_width, game.screen_height, stuff like that. So basically, if you must use globals, try not to make them naked. Give them a parent object if you can. Okay, so in the previous chapter, we made a function that creates rectangles. In this function, we could have made the variable rex local, since we only use it in that function. We will still use that rectangle outside the function, but we access it from the table list of rectangles to which we add it. We don't make list of rectangles local because we use it in multiple functions. So we could make this local. Though we could still make it local by creating the variable outside the loveload function. So like this, we can access it everywhere in this file, but if we're running multiple scripts, the other scripts won't be able to access this unless we explicitly send it to them. So, that's good to know. So, are there moments when it's okay to use globals? I think I made my opinion on that clear. I think it's okay to use globals sometimes, but you want to give them a parent object. A parent table in this case. So they're not just floating around in space. You know where they are. They're categorized. You know where to access them. And you can have multiple namespaces. So you can have variables with the same name, but they're stored in different places. So one game.x is not the same as, say, enemy.x. If that makes sense. You store things in different places, so they're not out in the open. Okay, now we're going to briefly go over libraries. So a library is code that everyone can use to add certain functionality to their project. We're going to try to use tick by RxI. So I already prepared this stuff. So we have tick in this folder. You might not be able to see it since they're very small, but this file right here is tick.lua. So now we're going to tabula rasa this. We'll keep example around for now, but we're not going to use it from now on, I don't think. So first we load tick. So we have a library called tick.lua in our project folder. All we need to do to use it is require it. And different libraries have different ways that they're coded. So in this case, the script for tick returns something. it returns an object. So we require it and store the result in a variable. For some libraries, you just require them in the open and they do their thing. But this involves an object, so we load it into a variable. Notice how require doesn't have parentheses. This is because when you only pass one argument, you don't have to use them. So I can just do this. In the end, it doesn't really matter. So we put tick update in our updater. We go tick update with our DT. So now we can use the library. Let's make it so that a rectangle will be drawn after 2 seconds. So, draw a rectangle equals false. Tick delay function. Draw a rectangle equals true. And 2. We'll talk about what that's doing in a sec. So now we have the draw function love draw. If draw rectangle is true, then we want to draw a rectangle. So if we run our project here, hold on. Oops. I need an end there. Ta-da! It takes 2 seconds, but then a rectangle is drawn on the screen. So, what is tick delay doing here? Did we just pass a function as an argument? Sure, why not? Function is a type of variable. So when we run the game, we can put a delay on calling functions. And just like that, there are lots of libraries with all kinds of functionalities. So don't feel guilty using a library. There's no need to reinvent the wheel. Sometimes it's nice to learn how to do different things for yourself. It can give you a little perspective, so even if you use a library down the line, you'll better understand its strengths and shortcomings. So libraries aren't like magic spells, they're just other people's Lua code. Sometimes they're identical to stuff you'd write yourself, you just save time using them. So, Lua has a bunch of built-in libraries. They're called the standard libraries. These are functions built into Lua. Print is part of it, as is table insert and table remove. One important standard library we haven't looked at yet is the math library. It provides math functions, which can be very useful when making a game. For example, math random gives us a random number. We can use it to place a rectangle in a random position whenever pressing the spacebar. So, let's implement this code here. We will have X at 30 and Y at 50. We'll have a rectangle and draw. That is the line fill mode. Our X and Y variables, and is 100 by 100 for a 100 width square. Oop. And when a key is pressed, what we want to do is, if it's space, if K E equals space, then X equals math random between 100 and 500, and Y equals math random between 100 and 500. So, if we run this, I don't need this. So, every time we press space, the rectangle will be in a different position, randomly selected. Brinky. Okay. So, libraries are code that give us functionality. Anyone can make a library. There are also built-in Lua libraries called the standard libraries. So, now we'll go into classes. Classes are like blueprints. You can create multiple houses with one blueprint. Similarly, we can create multiple objects from one class. You can mess around with Lua and create rudimentary classes of your own, but they don't quite work like how you'd expect object-oriented classes to work. So you do kind of need a library for it. Or code your own type of class indistinguishable from a library. So we're going to use classic. And just like the other library, I have it already in this project folder. So we're loading classic into object. So now if we create a new file called rectangle Lua, we can extend out of object. And We're giving it a test property, and we load our script. Come on, get rid of that. That's annoying. There we go. So now we can print the properties we made for the rectangles. And what does this look like? So in the output, we have 795 and 699, which are just randomly generated numbers between 1 and 1,000. So, what is this doing exactly? Well, when you run the game, you'll see that 2 random numbers are printed. So, first we create a new class with rectangle equals object extend object. This makes rectangle become a class. This will be our blueprint. As opposed to properties, classes are usually written with an uppercase character. So this will be upper camel case or Pascal case. In main Lua, we say R1 equals rectangle. Even though rectangle is a table, we can still call it as if it's a function. How that works is for another chapter, but by calling rectangle, it creates a new instance. What that means is that it takes our blueprint and creates a new object with all the class's features. Every new instance is totally unique. It has the properties, but it has its own values for those properties. To prove that R1 is unique, we create another instance called R2. Both have the property test, but they have different values. So when we call rectangle, it executes rectangle new. This is what we call the constructor. The parameter self is the instance we're modifying. If we were to type rectangle test equals mathrandom 0 1000, we would be giving the property to the blueprint and not to an instance made with the blueprint. So we can make some changes to our class. And this is a lot of stuff, so what I am going to do is copy it and look at it. So we have a rectangle new self that has x, y, width, height, and speed. We have an update function, and we have a draw function. So this is a general idea with game objects. Objects that very specifically exist in the game world. You usually want each of them to have their own update and draw loops. And the program's main update and draw loops will then call these individual update and draw loops. So you have functions constantly calling other smaller functions, or local functions, I should say. So every rectangle has a draw function, and the game's draw function calls on each rectangle's draw function in turn. So it's like the moving rectangle object from chapter 8. However, this time the code of the movement and the drawing is in the object. Now we only need to call update and draw in main Lua. So in main, we can get rid of that. And we update ET. We want R1's update. And we draw. And when we run this, oh, that's right. This wasn't saved. Let's try that again. Rectangle Lua 16. Attempt to index local self. Okay. We need to give it itself as an argument. There we go. So now we've got that moving rectangle again. Love those moving rectangles. So we created a class called rectangle. We create an instance of that class called R1. So now R1 has the functions update and draw. We call these functions, and as first argument we pass the instance itself, R1. And this is what self becomes in the functions. It's kind of annoying though how we have to pass R1 every time we call one of its functions. Luckily, Lua has a shorthand for this. When we use a colon, the function call will automatically pass the object left of the colon as its first argument. So let's modify our calls to use that. R1 update and R1 draw. So now we get the same thing, except we've cut down a little bit of code. Looks a little more trim. And you can actually do this with the functions themselves too. So, rectangle new. Rectangle update. And rectangle draw. So, this sort of, I guess you would say, formalizes this function as a method of the rectangle class. So in doing so, it has access to all the instance properties. We call this syntactic sugar. Very sweet. Just like you. So, let's add some parameters to rectangle new. And this will allow us to initialize these properties when we create a new rectangle. So we can give R1 and R2 each their own position and size. So we just update and draw R2 as well. And what we should have is to move in rectangles, like so. This is what makes classes great. R1 and R2 are drawn from the same blueprint, but they are totally unique otherwise. So another thing that makes classes great is inheritance. With inheritance, we can extend our class. In other words, we make a copy of our blueprint, add features to it without editing the original blueprint. So this is sort of an example image. So on the left, you have a basic house with one story. However, you can take the fundamentals of that, make a new class that inherits from this class, and add a second story without changing the original blueprint at all. So, another example they give. Let's say you have a game with monsters. Every monster has their own attack and they move differently, but they can also get damage and are able to die. Overlapping features should be put in what's called a superclass or base class. They provide the features that all the monsters have. And then each monster's class can extend this base class and add their own features to it. So, we will create another moving shape, a circle. What will our moving rectangle and circle have in common? Well, they both move, so let's make a base class for both the shapes. We'll create a new file called shape.lua, and we'll put in this code. We'll copy and paste for that. Shape.lua. And look into this. So, just like last time, we're extending this shape. We're giving it a new function with the things that all the shapes will have in common, which is XY coordinates and speed, which is constant at 100 at the moment. And all of our shapes will have the same movement behavior. Default movement behavior, I should say. If they don't override this, they will all move on the x-axis based on their speed. So, shape now handles the movement. Now we have a base class. We can make rectangle extend from shape and remove extraneous properties and functions. So, first we require shape in main. We should be doing that before rectangle, because remember, things are loaded in order. So now in our rectangle, instead of extending off of object, we can have it extend off of shape. And that will set up our inheritance. So now instead of this stuff. What this does is it's calling the parent class. So rectangle.superNew means use shape new instead of rectangle new. In addition to, I should say. So this is setting up everything that occurs within shape, the shape object's new function. So this sets x, y, and speed. So we do not need to set x, y, and speed in the rectangle function if we use this call. We can get rid of this too. Okay. And we don't need that update anymore because we don't have overriding behavior. This just behaves like a shape behaves. We do keep the draw though because rectangles are drawn uniquely to other shapes. So, what haven't we gone over? Rectangle has the property super, which is the class that rectangle is extended from. So in that case, it is shape. So we do have to pass self as the first argument because we can't use a colon there because we're not calling the function as the instance. So now we create a circle class. I'm going to copy and paste this stuff into it. Circle.lua. And if we inspect this, a circle also has a radius. A rectangle didn't have a radius, but a circle does. And when we draw it, instead of using the rectangle call in LÖVE, we use the circle call. And we give it the x, y, and radius. Very simple. Okay, so now in our main, we will need to require circle as well. Just like that. And I'm actually going to make an additional circle. C equals circle 20, 140. And we'll give it update and draw. So when we run this, we should, yeah, we see rectangles and our circle. Excellent. So I believe I've gone through all the code, so we don't need to do that. Okay, so that was a lot of information. So feel free to take some time to take it in, especially if you are on YouTube, you have the ability to pause and rewatch sections of this. And if I remember to, I will go back into the VOD posted on the YouTube archive, and I will make sure that these sections are divided up neatly, so you'll be able to skip through them and rewind back if you want to watch a section over again. So that's something I will try to remember to do for you guys. Okay, so in summary, classes are like blueprints. We can create multiple objects out of one class. To simulate classes, we use the library classic. You create a class with class name equals object extend. You create an instance of the class with instance name equals class name. This will call the function class name new. And this is called the constructor. Every function of a class should start with the parameter self, so that when calling the function, you can pass the instance as the first argument. Instance name dot function name instance name. We can use colons to make Lua do it for us. So we can extend a class with extension name equals class name extend. This makes extension name a copy of class name that we can add properties to without editing class name. If we give extension name a function that class name already has, we can still call the original function with extension name.super.functionName self. Okay, that's a lot of information. So, images. Creating and using images is a very easy task in LÖVE. First, we need an image. We're going to use this image. I have it in the project folder. So, first we need to load the image and store it in a variable. For this, we will use LÖVE graphics new image path. Pass the name of the image as a string as first argument. So, we use load take my image and put the sheep in that variable. You can also put your image in a subdirectory, but in that case, make sure to include the whole path. So now that we have that stored, we can use draw to draw our image. LÖVE graphics draw, and we want to draw my image at the coordinates 100 by 100. And if we run this, we have our image right here. So let's take a look at the arguments of LÖVE graphics draw. All of them, apart from the image, are optional. So, image is the image you want to draw. X and Y are the horizontal and vertical position of where you want to draw the image. R is the rotation or angle. All angles in LÖVE are radians. SX and XY, SX and SY are the X and Y scale. So you can make the image twice as big if you set it to 2, 3 times as big if you set it to 3, half as big if you set it to 0.5, etc. And you can also use it to mirror an image by using negative values. So, OX and OY are the X and Y origin of the image. So, by default, all the scaling and rotating is based on the top left of the image. That's the origin. If you want to scale or rotate the image from the center, you put the origin in the center of the image. KX and KY are used for shearing. With it, you can skew images like this. LÖVE Graphics Print, which was used to draw text, has the same arguments. So, the image that LÖVE Graphics new image returns is actually an object. An image object has functions which we can use to edit the image or get data about it. You can use getWidth and getHeight to get the width and height of the image. So for example, you can use this to put the origin in the center of your image. So in this code, you load an image, you set the width to the width of the image, set the height to the same, the height of the image, and then in the draw, you put the draw origin in the center by saying width divided by 2 and height divided by 2. And that position would be the center of the image. So you can also change the color the image is drawn with LÖVE Graphics Set Color. So it will set the color for everything drawn and uses the RGB system. However, the RGB will range from 0 to 1. So, if you want to use RGB, you have to divide your number by 255. There's also the fourth argument A, which stands for alpha, and this decides the transparency of what gets drawn. So it's generally good practice to set the color back to white either at the end or the beginning of a loop. So that way your color choices don't get reflected in other draw calls. So in summary, you load an image with my image equals LÖVE Graphics new image, and this returns an image object that we can store in a variable. This variable can be passed to LÖVE Graphics Draw to draw the image. This function has optional arguments for the position, angle, and scale of the image. An image object has different functions you can use to get data about it. You can also use LÖVE Graphics Set Color to change what color the image and everything else is drawn. So, if you use Set Color, it will color everything until the next set color. So that is something to keep in mind. Okay, detecting collision. I think this will be the last tutorial we do for tonight. I'm a little sad we didn't get to, like, real game stuff, but that's kind of what happens when you're going through programming tutorials. You have to learn every basic concept all over again. And that can be time consuming. This tutorial is pretty good, so it's getting us through it fairly fast. But programming can be hard to learn, and if you tuned out because you didn't really understand it, if you're kind of confused and don't know what's going on, that's totally understandable. You probably won't get everything the first time you hear it. If you're totally new to all this, me talking to you about it probably won't immediately help you understand. But if you do stick with it, you will get it eventually. At some point, it usually just starts clicking, and you start understanding what's going on a bit. But anyways, let's get through this last tutorial together. So, let's say we're making the game where you can shoot down monsters. A monster should die when it's hit by a bullet. So, what we need to check is the monster colliding with a bullet? We're going to create a collision check function. We'll be checking collision between rectangles. This is called AABB collision. So, we need to know, when do two rectangles collide? I created an image with 3 examples. Boop, boop, boop. It's time to turn on that programmer brain if you haven't already. What is going on in the third example that isn't happening in the first and second example? They're colliding. Oh yeah, but you have to be specific. We need information that the computer can use. Take a look at the position of the rectangles. In the first example, red is not colliding with blue because red is too far to the left. If red was a bit further to the right, they would touch. How far exactly? Well, if red's right side is further to the right than blue's left side. And this is something that is true for example 3. But it's also true for example 2. We need more conditions to be sure there is a collision. So, example 2 shows we can't go too far to the right. How far exactly can we go? How much would red have to move for the left for there to be collision? When red's left side is further to the left than blue's right side. So, we have 2 conditions. Is that enough to ensure there is a collision? Well, no. Look at the following image. This situation agrees with our conditions. Red's right side is further to the right than blue's left side, and red's left side is further to the left than blue's right side. Yet, there is no collision. That's because red is too high. It needs to move down. How far? Till red's bottom side is further to the bottom than blue's top side. But if we move it too far down, there won't be collision anymore. How far can red move down and still collide with blue? As long as red's top side is further to the top than blue's bottom side. Now we got 4 conditions. Are all 4 conditions true for these 3 examples? Red's right side is further to the right than blue's left side. Red's left side is further to the left than blue's right side. Red's bottom side is further to the bottom than blue's top side. Red's top side is further to the top than blue's bottom side. Yes, they are. Now we need to turn this information into a function. First, let's create 2 rectangles. So we'll copy this into our main. We create 2 rectangles here. We update to make one of the rectangles move and draw. So what does this look like on its own? It looks like this. At some point, the moving rectangle R1 collides with R2. Now we create a new function called check collision with two rectangles as parameters. First, we need the sides of the rectangles. The left side is the x position, and the right side is the x position plus the width. Same with y and height. Okay, so the right hand is the x value plus the width. And the y value is y plus the height. And this is the same for RB. Okay, so we have the left, right, top, and bottom for both A and B. So we can use them to put our conditions in an if statement. So if A right greater than B left and A left less than B right, and A bottom greater than B top, and A top less than B bottom, then return true. Otherwise, return false. We don't need that. There we go. Okay, so here we will set the draw mode based on whether they're colliding. So we have a local mode. If check collision between R1 and R2, then the mode should be fill. Otherwise, the mode is line. Boing. And we replace these with the mode. Okay, excellent. So, what's this all look like? Well, hold on. Hmm, this needs an end. Okay. Ta-da! So, what's our logic doing here? So, if the right hand side of A is greater than the left hand side of B, and the left hand side of A is less than the right hand side of B, and the bottom side of A greater than the top side of B, and the top side of A less than the bottom side of B, then they're colliding. We have four separate conditions interlocked that results in a detection of collision when it goes through. So, that is collision detection using Lua programming and visualized in the LÖVE framework. Okay. I think now is a good time to wrap up. Today, I don't blame you if you were a little bored. We've been going through an almost entirely text-based medium. We don't have a fancy visual editor that looks nice and fun. We've just been typing on our computer all day. But I thought it was important to do at least one purely text-based game framework, because I kind of don't want people to be intimidated by programming. It's not as hard as it sometimes seems. It's something that understanding this comes with practice. It comes with taking in the perspectives of multiple people who teach it. And yeah, it's just over time, as you practice, you'll get a more intuitive sense of logic, and logic is really the fundamentals of what it's all about, even when you're using a visual editor. So, all that I kind of want people to realize is that those visual editors are just sort of abstracting away the things that we've been doing here today. Like, when you're using a visual editor, you're still kind of programming. You're just programming using pieces that the engine already made for you. You're doing a lot of the same things that we did here with collision detection, with image drawing, with shape drawing. It's all sort of very similar. So when you're using Game Maker, Godot, GDevelop, you're just programming with a very specialized interface. So you shouldn't, if you're comfortable doing that, you shouldn't feel too intimidated by going into the raw code. There's stuff you can do to sort of supplement it. There are programs available like CastleDB and Tiles that can, for example, allow you to make tiled maps that you can then import through whatever standards each programming framework has in order to combine a little visual editing with raw coding. And there's other things like that you can do. When you get really good at these frameworks, you can actually code up your own editors, and they can actually be part of your game engine. They can be sort of debug structures that you can't really access in release, but are there when you are in the development stages. So, we've used the LÖVE game framework today mostly to demonstrate logic and mathematical aspects of the engine. We haven't quite gotten to making a good game with it yet, though. But I think this is a good place to start if you're wanting to get into a framework that will involve mostly programming. I think this is a good learning tool for that. It's powerful enough that you can make commercial games with it. I do not know how easy it is to make really big projects with it, though. And that's the thing with a lot of these engines. Like, you never know what the breaking point will be until you get there. And then by then you've usually spent a very long time, you sunk a lot of hours into learning and using the engine. And then you come up against a brick wall and you're like, ugh, what the heck? So, yeah. This was the LÖVE game framework. I recommend it if you want to do a pure programming approach. But if you want a visual editor, I would stay away from this one. This is for people who want to learn programming. So, the catch, as I discussed earlier, is that visual editors are programming too, just abstracted and with some things that help you get started faster. So I wouldn't be too intimidated by this. I would give it a shot if you want to learn a little bit of programming. It will be very fun to use. I have used this in the past to make a demo for a game jam before. It was pretty fun to use. I'm sure I didn't use it very well. I'm sure my programming was very bad at the time. It's been improving, but I am not an expert by any means. So, that was today's Let's Make Games. And for tonight, I will be signing off. It's been gay.